In this lesson, we're going to talk about the one component phase diagram, and in particular, we're interested in talking about the phase diagram of water. When we look at the simple water diagram, we see lines on the diagram, and those lines have specific meanings. What they do is they separate boundaries with respect to phases. So each one of these lines on this one component phase diagram represents a boundary that separates two regions, and hence these lines are two-phase fields. They describe the variation with respect to, in the case that we're working with water, they're describing the variation with respect to the solid phase, the liquid phase, and the vapor phase. And so in those open regions where we have solid and liquid and vapor, those regions are single phase. That is, regardless of what the pressure and temperature are, we will find when we are inside of those single phase fields, the only phase that is present is the phase that's indicated. However, when we come and approach those lines that separate the single phase that represents single phase boundaries, where we have a solid and a liquid phase in coincidence, then what we have is two-phase equilibria, namely the solid and the liquid are in equilibrium. And we can then begin to understand how all of these diagrams come together. So the three lines that are indicated are the solid liquid, liquid vapor, and the solid vapor equilibrium. We also have, in addition to the single phase solids and the two-phase regions of solid vapor, solid liquid, and liquid vapor, we have a point that we refer to as a triple point. At that one point on this diagram, it tells us that only the solid phase, the liquid phase, and the vapor phase can all coexist together, and that has a fixed pressure and it occurs at a fixed temperature. Now, what we often do with respect to the water diagram is to consider what's happening at 1 atmosphere pressure. And when we talk about 1 atmosphere pressure, what we're doing is we describe, when we have the transformation to the solid phase to the liquid phase, what we do is we refer the temperature that transformation is occurring as the normal melting temperature or the normal freezing temperature, because it's done at 1 atmosphere. As we continue along and we wind up increasing the temperature at 1 atmosphere, what we then do is we reach the boiling point, and this is then defined as the normal boiling point. Now, if we take a look at some pressure P1 and we extend it over to the phase boundary that separates the liquid phase from the vapor phase, what we know is at that particular point on that boundary, we have defined immediately, as a result of choosing the pressure, we have immediately fixed the temperature in the system. Once we say that we are in a two-phase liquid vapor field, we know that by fixing the pressure in that field, we automatically fix the temperature, and that temperature then is given as T1. So when we look at the phase rule, which was written down by Gibbs in the early part of the 20th century, what it's telling us is that we have a parameter that we refer to as F, and that's the number of degrees of freedom. We have the number of components C, the number of phases that are present, plus 2, and in this case, the 2 corresponds to the two thermodynamic variables of pressure and temperature. Now let's go back and think about what we mean by the degrees of freedom. Let's say that what we have are a system of equations in X, Y, and Z, and so it's a first order set of simultaneous equations. Now, if we have all three equations, then what we know is there are no degrees of freedom in that the system X, Y, and Z that satisfies that set of equations is completely fixed. Now, if we would take and erase one of those equations, then what would happen is we would lose one of our variables, and what we would then need to do is to fix the next variable. So let's say we fixed the value of X, then when we put the value of x in the last two equations that we have, we would then be able to come up with the values for y and z. So we would say we have 1 degree of freedom. So we have the ability to choose one of the values of x, y, or z. Then when we come down to taking away 2, then what we have to do is to talk about 2 degrees of freedom. In other words, before we can solve any one of those equations, we have to fix the values of x and y, and once we've done that, then what we can do is determine what the value of z is. So this is what we mean by this idea of the degrees of freedom. Let's return to the water diagram again. And this time we're going to think of the water diagram in terms of the Gibbs phase rule. Remember that the Gibbs phase rule says that we have the degrees of freedom, the number of components, the number of phases, and the pressure and temperature in the system. Now, when we talk about all those open regions, which are the single phase field, we have 2 degrees of freedom. What that means is I have to tell you both the pressure and the temperature for you to be able to determine where you are on that phase diagram. So if I tell you that you are in a solid phase field, then I have to give you inside of that solid phase field pressure and temperature. Now that then describes the degrees of freedom for a single phase field. Now when we look at the boundaries that separate these single phase fields, these are the regions of two-phase equilibrium, they now tell us that we have 1 degree of freedom. And what we mean here simply is that once we fix the pressure or the temperature along one of those lines, we automatically have determined the thermodynamic variable of the other. In other words, if we describe the pressure in the region where we have liquid-vapor equilibrium, and we know, therefore, once the pressure has been determined, we know exactly what the temperature is. So that tells us that we have that single degree of freedom. Now when we look at the situation where we have 3 phases in equilibrium, that is, F is now equal to 0, that tells us what happens at this particular point on the diagram. Once I tell you that you are at a triple point in a 1-component system, you automatically know where you are when I tell you the particular phases that are in equilibrium. In other words, ice, water, and water vapor. So once that's been established, we know that we are at that specific point. Let's continue our analysis of the diagram. Let's focus on the 2-phase region that's represented by the line describing the boundary between the liquid phase and the vapor phase. When we look at the liquid vapor line, we can describe, for example, 2 different points. One point that tells us a given pressure, namely pressure P1, and when we look at pressure P1, what we see is, correspondingly, a temperature T1. So we've then defined the relationship between P and pressure and temperature for this system, and because we fixed the pressure, we automatically know what the temperature is. Now, this diagram that we're describing is a diagram that talks about the 2 variables, the variable pressure and the variable temperature. There is, however, an additional plot that we can make where we describe the relationship between the pressure and the volume. And what we're going to do is come up with the pressure volume diagram, and we're going to focus on the pressure at P1. So when we look at pressure at P1, because we have fixed the pressure, we immediately know that we have a temperature T1, and what we can say is at T1, we have what we refer to as a saturated vapor pressure. Now, we know also that that horizontal line that describes the volume of the phases that are in equilibrium, when I look down along the x-axis of that plot, my 2 phases that are in equilibrium are determined by the volume of the liquid and the volume of the vapor. So we have our saturated vapor pressure, we have our region of two-phase equilibrium, and the boundary of the two-phase equilibrium is the points that are indicated on the diagram. And depending upon where we lie between the volume of the liquid and the volume of the vapor, we're going to have different ratios of those two phases. Now we know that we are along an isotherm because at pressure P1 there is a corresponding temperature T1. So these then give us a way for us to begin to think about the pressure, temperature, and now volume diagrams. One thing that we should point out is that pressure and temperature are both intensive variables and do not depend on the size of the system, whereas volume is an extensive property, and we need to specify how much of the material that we're actually looking at. Thank you.